Okay, so maybe you are always wondered how you could do Jedi mind tricks with a computer, and that's exactly why we are here now. So Gnudi is going to tell you fundamentals of EEG-based brain-computer interface, and he's always been fascinated with the human brain, and he is a researcher in that scope, and I give the stage to you, Gnudi.
Hello. The reason why I'm giving this talk is recently there has been development in electroencephalography. That was developed about 100 years ago and has been used in research and in medicine as well. But we now have consumer-grade EEG headsets as well as some open hardware projects aiming to develop EEG headsets. There I have a picture of the Emotive Epoch, which I think was the first consumer-grade EEG headset. And actually, I think the aim of the OpenBCI project is to get cheap research-grade hardware. I'm not going to explain too much about the devices. I want to talk a bit about how we can use EEG readings to have a brain-computer interface. A brain-computer interface typically consists of a user having a task. The task can be thinking, for example, to have some input. If it's used to drive an electric wheelchair, for example, it could be a thought to go forward. The signal has to be the EEG signal has to be acquired. I'm not going to talk about that. I'm more focusing on the pre-processing of the data and the feature extraction. Classification can generally be done with all kinds of classifiers. Popular are support vector machines. But a good feature extraction is essential. We cannot really do machine learning approaches where we learn the features because we typically do not have very much training data. Doing EEG experiments with human subjects takes a lot of time, and also the data might contain private information, so often the data sets are not made public. So yeah, that's what I'm going to talk about mainly. But generally, after classification, we have an output translation. It can be a virtual keyboard or something. And there can be, that is optional, a feedback that allows the user to train the brain-computer interface. Here I'm showing you the timeline of an EEG signal. This was a resting state experiment, so the subject was just resting, doing nothing with eyes open. You can't see very much in the timeline. It looks quite random oscillations, quite low. Generally, the signals are in the millivolt range. So one of the first steps that you can do a time frequency analysis. So what we have here is we have 14 seconds of EEG and 14 electrodes. That's the 14 channels that the Emotive Epoch EEG headset has. And here we also have 14 seconds, and this is basically doing couple of computing spectra for different time slots. So you see the development of the spectrum over time. And what you see here is one of the things that make it difficult. Most of the signal power is in the range below 5 hertz. The different frequency ranges are typically associated with, for example, some states of mind, like sleep states. Actually, it's quite easy, even with the timeline, to see in which sleep state someone is. Important is the alpha band. That's something that should be in the plot that I showed before as well. We couldn't really see that in the timeline. If actually I had instructed the subject to have the eyes closed but not open, we would have seen oscillations in that range on the electrodes that are above the visual cortex, because they would go to idle state if nothing is seen, and we would have more power in there. If we are doing EEG experiments, we typically look into changes, because we have this huge random noise signal where we have basically no idea what it means. We typically have experiments where we look at some at least two different states. So we define something as a baseline, and then we typically look at what changes if we, for example, we have a resting state task for the subject, and then the task is to think maybe the command to move the wheelchair. What we see here is, again, from the same EEG recording. What I did was I used the 2 seconds before that are not plotted here, but it looks about the same. Computed the average and divided it all by it. We call that baseline correction. So now it's easier to see changes here in the other areas. So having a baseline is something that you normally do if you have some EEG experiments. We also have some other problems besides the general background noise that we have. It's artifacts. Here it's a similar timeline. The difference is the subject was instructed to blink in intervals. You see that there are some huge peaks there, especially on the lower and the higher lines. That's because, according to the 10-20 system, the electrodes are numbered around the head. So on the top and on the bottom, it's basically the electrodes on the forehead. So what we see there is eye artifacts. Actually, to see artifacts, that's quite easy in the EEG timeline. The problem is getting rid of it if we don't want to have it. So we start typically by instructing subjects not to blink, not to move. Also a problem can be having, for example, the 50 hertz power grid can also be an artifact in the signal. Therefore, we typically have filters at that frequency. There are different approaches to get rid of the artifacts. The simplest one is cutting out of the data the parts with artifacts, but this basically means we have to repeat the experiment to have it several times. But we are doing that anyway. If we one approach for brain-computer interfaces are event-related potentials. If we have an event, that could be a subject is shown a picture or any other stimuli, and we repeat that, and then we average over all the repetitions of showing this image, then all the random noise will cancel out, and what we are left with is the EEG component that actually depends on the processing of showing this image. And that we call an event-related potential. This is just an example. Typically, it doesn't look that nice. We typically count the peaks. So we have 3 positive peaks here. We call P1, P2, P3. And the P3, or also called P300 because it's about 300 milliseconds after the stimulus, that is something that we use for brain-computer interfaces. Because there's the so-called oddball paradigm. The P300 is only there if something is relevant to your task and it's not happening very often. So the P300 speller, which is something like a virtual keyboard, unfortunately I don't have an animation, the lines and rows would light up at some speed. If you want to type a letter, you would focus on a letter, and when it lights up, that is a rare and relevant event to you because you want to type it. So exactly in that case, you will have the P300 in your ERP, and of course the system that is providing the stimuli is recording the timing and then knows which letter actually was lit up when this appeared. So this way you can type things, but again you would need to stare at one letter for a while because it has to be repeated several times. So I want to present more specialized P300 based brain-computer interface that is an authentication scheme. The idea is we are having 100 normal photos, can be anything, and we select some which are our password. So this is the example that is actually a set that we use for the experiment. 5 very different photos. So now I'm doing a small experiment with you. Try to remember those photos and try to see them and count them in this video stream. So I think I'm not asking you to raise your arms because I can't see you anyway. I guess some of you might have seen all 5 pictures, some might have counted less. For the first time the task is not really easy, but generally when in this experiment you counted something, you will probably have had this P300 in your brain. Those are the results of the experiment. I hope you can read it. Might be a bit too dark. As we have 95 non-target image and only 5%, so 5 target images, we use the F1 score to evaluate the classifier. We did cross-validation on the data here, where we have the best score. We also did train the classifier, which was a simple linear discriminant analysis. We trained it just by the experiment done by one person, and then we also tried to do a general classifier that we trained with other people's data. For that we used the best data sets that we have that had the highest score in the cross-validation. It still works. The interesting thing here is that the classification of the EEG data is possible without tuning the classifier to the user, making the system non-biometric. This is the number of trials that we averaged. So we actually showed 50 of those bursts that you have seen just before. that takes about 20 minutes, and no one wants to use an authentication system where one login takes 20 minutes. So we looked at how many bursts do we actually need, but it seems like up to 50 it still increases. And there's a huge difference between different sets. So the highest line is the top rated subjects, and the others are much lower. So it depends a lot on the subject, maybe also on how well the EEG headset fit, and of maybe how well they focused on the task. But it's the biggest effect that we found was for an authentication system, we want to have permanence. So if we want to log in again after a few months, it should still work. So we had 3 sessions with some months in between. And actually we got better scores over time. We feared that they might degrade, but it seems there's a training effect. And the signal is permanent enough. So here is the final score. That's a plot, because even though it's no real biometric system, we are measuring biosignals, and that can go wrong. Therefore, we have false acceptance rates and false rejection rates, and we are coming to an equal error rate of about 10%, which is, of course, too bad, especially when you see that one authentication round takes about 20 minutes. So the idea was, if we have if we are showing the images very fast, we can have a very short login time, but it actually didn't really work well enough. And that's it. There are 3 minutes left. Are there questions?
Nerdy. I found my voice again. So, indeed, we have a bit of time. There are 2 microphones and the internet. So remember, and there's a question at that microphone.
Hello there. I was wondering, have you heard of this being used to detect terrorists? There was an experiment done where they showed images of things that you're not supposed to know as a regular citizen. So they would show all these innocent images, and then there would also be a blasting cap or the magazine of an AK-47 or stuff that you're supposed to know if you went to a terrorist training camp. And they would do the exact same P300 thing. I thought that was interesting. And of course, if you read about training camps and terrorists, you would fail the tests, which would be interesting.
Yeah. I haven't heard about the application on terrorism, but very similar, the application on criminal investigations as a lie detector based on P300. So basically the same. You are showing some pictures that only the
guilty knowledge tests.
That only the one who's guilty knows, and but there are also some papers about if you are attacked by this P300 based guilty knowledge test, how to prevent being detected.
Okay, another question. That microphone.
I have 2 small questions. One is, which was the EEG headset used in the image-based authentication? Was it the OpenBCI? And then also, is P300 individualized? Like, does it need a lot of calibration, or is it something that you can just detect straight in?
The EEG headset used for the experiments was the Emotive Epoch, the P300 seems to be a bit individual. There are approaches doing biometrics by looking at the P300, but our approach was to have a general P300 detector that would work on anyone. That was the difference between the IC, the individual classifier, and the GC, general classifier. You can see the score difference here, the middle and the right one. And the left one was the cross-validation.
Okay, is there a question from the internet? I'm looking at no question from the internet. So unfortunately, the time is running out, and so I have to ask you to approach Knödi directly. And I don't know, you're here, you're at the Congress, and can be contacted in some way, I guess. Okay, then I would say thanks Knödi again for his talk.
Mm-hmm.